So before we get started on that, I was browsing through our company Slack and found that we have this really old channel on our Slack called Semaphore. And as someone who's really interested in locking systems, and especially distributed locking, it sounded intriguing, sounded something like something I should look at. Reading more into it, the purpose of this channel was to coordinate access to 10 remote access machines to access particular banking data for our customer operations in the really early days. Staff members would go into this channel, declare a lock between 1 and 10, and then use that corresponding machine. This was necessary for a bunch of boring reasons that were totally not our company's fault. It was a third party. These machines had single access use only. And if you logged in while someone else was logged in, you would get kicked out. And it would terminate all the queries that you were running. People were pretty fast in acquiring these locks, but very often forgot to release them. So we need to tackle this as a problem, unless otherwise you want to go beg and plead your colleagues to release their locks when they're done. So you guessed it, we put in a 4 a.m. auto-release of all locks. So if you were running a query past the 4 a.m. boundary, you had to make sure that you quickly got in and reacquired your lock before someone else takes it. I just love the chaos that's involved in such a system. Happily, we've grown a lot as a company, and we've applied a lot more engineering expertise to this, and we've gotten rid of all of those 10 machines and indeed this entire system. So yeah, now on to the main program. We're going to spend the next 20 minutes talking about service discovery and how most of the time you should consider having systems which are eventually consistent when they do their service discovery, and some of the pitfalls if you choose something else. Bit of an introduction. My name is Suhail. I'm an engineer on the platform squad at Monzo. Monzo is a bank. We are a bank in the UK with over 3 million customers. We are now also operating in the US for any folks from the States. We've just recently launched in the US. On the platform squad, we build the foundation so that other engineers can ship their services and applications without having to worry about whether their deployments are up and running or whether the database is performing well. Most of the things it involves debugging things like Kubernetes, Cassandra, Envoy, and other distributed systems. Like I mentioned, we are a fully regulated bank in the UK with 3 million customers who trust us with their money. Our mission is to make money work for you as a customer. We also have these really nice looking hot coral cards. We have a few with us. There's a few Monzo people in the crowd. They don't exactly glow in the dark, but they're the next best thing. So the inspiration of this talk came from some discussions about always defaulting systems to strongly consistent service discovery. It makes systems easier to understand, easier to debug, if every component has the same view all the time. The goal here is to talk about some of the kinds of consensus systems out there, discuss the various approaches you can take, what works with thousands and potentially even millions of clients. So let's take a step back. What do I really mean by service discovery? Say you have a database like Cassandra. When you're first running it with just a single node, one node, it's running solo. You're reading all of your data from this one node, and you write all your data to this one node. You give it a fixed IP, a deterministic port. You might give it a DNS name, because it's not going to change. And it's just one node. There's nothing to discover from your service point of view, from Cassandra's point of view. All your data is in one canonical place. And all the decisions are made in this one node in isolation. And all is good in this simple world. Now, typically, that's not how you run a data store like Cassandra. You run Cassandra with multiple nodes, and this applies to a large majority of distributed systems. You run with multiple nodes, and they coordinate with each other to take advantage of things like high availability and replication. You don't want a single node failure to cause your entire database to go down and lose all your data. Each of these other Cassandra nodes needs to know where a particular Cassandra node is to form the cluster. So this involves exchanging things like IP and metadata and doing health check and whether something is up and running. So what service discovery boils down to is, for a set of members, how do you automatically detect the ones which are present, alive, and are able to serve requests, conduct an action? You might have also heard of it as a membership protocol. Now, what if one of the nodes goes down or fails all of a sudden? Now, service discovery often encapsulates things like active health checking or heart beating to detect if a node fails or if part of the system is degrading, leading to loss of performance. So this is so that if you hit a particular node and you know that it's degraded or down, you don't send your request to it and have it inevitably fail. You can route around that smartly beforehand in a timely manner, but not picking nodes that are down or have really high latency. So what does strong consistency mean, and how is it typically implemented? And I'm going to explain that a little bit by talking about a system called Etcd and a little bit about the Raft protocol that it uses under the hood. So for those who don't know, Etcd is a very popular distributed key value store. It's used for a wide variety of reasons, for storing metadata about anything, to be honest, in a key value fashion. A good use case would be for Kubernetes, which uses Etcd to store all of its cluster data, like, for example, what deployments exist, what pods exist in your infrastructure. So under the hood, Etcd uses a consensus algorithm called Raft to implement its distributed consensus. It's a fancy way of saying agreement between multiple nodes. Raft is actually an acronym, which I found out whilst writing these slides, for replicated and fault tolerant. The goal is to develop an algorithm for agreement between multiple nodes, which is easily understandable and easier to implement than other similar algorithms like Paxos. I only found out that the Raft project has a logo quite recently. And it's not often that you see an algorithm with a logo, but I think it looks good. So in Raft, the nodes start off by electing a leader. And in this animation, you can see that the nodes are exchanging messages to become the leader. Any node can propose to become a leader by putting itself forward as a candidate and pushing out messages to garner votes to become a leader. A majority of nodes must agree to support this candidate for its leadership. And if a node has agreed to support a candidate for its leadership, it can't change its vote for that particular term. So unlike most human politics, computers usually play by the rules. In this example, the node S5, which is on the left-hand side, gains the leadership and starts its reign as the supreme overlord of this system. Now, let's say that you're a client application, and you want to write a value of foo and make it equal to bar. All of your operations will inevitably go through the leader. Again, this changes based on the implementation, but the leader is always involved in writing and usually with reading of data as well. So the leader in this case, which is S5, will reach out to all of the nodes to commit this change and only accept it in a scenario where the majority also agree to commit this write for foo. The leader does writes to all of these nodes for redundancy. If a leader fails or drops out, another will contest its reign and pick up where the leader left off. All actions which require consistency have to go through the leader. So that includes the majority of read and pretty much all write operations. They have to go through the leader. Now, let's put this in the perspective of service discovery. Every change goes through the leader in this process for writing of data. So say a replica in the hypothetical account service in red spins up. It can register itself with a particular IP and other metadata, and it can heartbeat at a particular interval. Another service, let's say the transaction service in yellow, can query for events and get the current state of things that are registered and when it was last heartbeated into the system via the leader. It can know that this replica of the account service exists for back and forth communication and available at a particular IP. Now, this kind of system sounds ideal. All of your clients can query this system and consistently get the same view because it's the leader which is providing all of this data. It's easy to debug because everything has the same linear, consistent view. If a bunch of your replicas query the leader at exactly the same timestamp, or even with a small amount of deviance, they'll still get the same data. Now, things start to get a bit hairy when you have lots of clients registering and lots of clients reading at the same time, and lots of clients watching as things are going on. Each node needs to commit each write to a log on disk. And to do this durably and reliably, which is one of the things that systems like Etcd promise, you can't just keep this log buffered in memory infinitely. You need to, otherwise a machine failure would lose data. Each write needs to be committed and persisted to disk. So those running Raft-based systems obsess over low-level metrics like this. This is showing disk commit duration using a particular syscall called fsync. They get a little bit worried when they see an uptick in this graph because that means that all of their writes have slowed down. This graph directly correlates to how many concurrent writes you can have. So if you're looking at things like requests per second, how many things you can serve, you are very worried about things in this graph. In the read path, again, the leader will have a much larger disproportional CPU usage compared to the other nodes in the cluster. The other nodes in the cluster are only there for redundancy. Most of the operations have to go via the leader. Now, of course, depending on the implementation of Raft, you can optimize this further. There's been a bunch of work by HashiCorp to optimize the Raft algorithm to make this better and make all the other nodes proportionally use CPU and disk usage. Let's talk a little bit about sequential consistency. This is one rung down from strong consistency. And to really explain, I'm going to use examples from Zookeeper. And for those who haven't really worked with Zookeeper, it dubs itself as an open source distributed coordination server. So in layman's terms, it's pretty much very similar to what you see with Etcd. It's good for keeping metadata and configuration in a distributed fashion, similar to what we saw with Etcd. Zookeeper is pretty neat if you haven't used it before, because it exposes itself with an API which is quite similar to a file system hierarchy. You can actually do an ls command. So you can do like ls/app1 and get all the things beneath it, like p_1 and p_2 and stuff like that. So it's quite flexible. It's quite neat. Similar to Raft and Etcd, leader is elected in Zookeeper, and writes go through the leader. Zookeeper uses its own protocol called ZAB, Zookeeper's Atomic Broadcast Protocol. And where Zookeeper is slightly different is that reads can be served completely through any node without any direct interaction with the leader. The entire protocol is built on a concept of state machine transitions. So what that really means is that the leader is writing to quorum. So it's writing to a majority of nodes in the cluster. So here we have 5 nodes, and to achieve quorum, it would write to 3 out of the 5, including potentially itself. But this does mean that for a small period of time, if you're querying the other 2 that haven't reached quorum in that period of time, they could serve stale data if they haven't caught up with all the writes. It's called sequential consistency because it doesn't matter what node you read from, an update won't be presented out of order. If you have an update that was presented a particular timestamp, like T3, it will definitely have the update for T2 and T1. Now, again with Zookeeper, running a cluster of Zookeeper instances means you have a central repository with a leader, which you need to operate and optimize for. Every state change needs to be stored and tracked, and you're going to have disproportionate usage on the leader itself. Zookeeper provides plenty of knobs and consistency options to allow you to tune this and the level of consistency that you really want. Dropbox has a really good talk from SREcon in America in 2019 on the challenges of scaling their service discovery, which is built on top of Zookeeper, with millions of clients and tens of thousands of state changes a second. So we've spent quite some time talking about strongly consistent systems. Let's talk a little bit about eventually consistent systems. Has anyone played this game called Plague before? There's also a board game version called Pandemic, which is sort of the opposite scenario. So what Plague is you develop a virus and you give it particular points to level it up, and the goal is to infect the entire world before the hypothetical doctors that are the AI come up with a cure. And in Pandemic, which is the board game, it's quite a similar game, but you're on the side of developing a cure for this hypothetical virus-based scenario. This is quite relevant here because a lot of the widely used eventual consistent systems are built upon gossip and infection-style protocols. So in a gossip-style system, a node would typically be connected to a handful of other nodes. When a change comes in, or when you want to propagate a message, you talk to your peer nodes, and they will gossip their changes onto their peers. Depending on the implementation, you might have a fixed set of alive players, or you might pick the ones with the lowest latency, or the ones in the same data center as you, or you might just pick a random subset of nodes in the cluster to message and coordinate with. Gossip messages will typically be sent to peers at a particular time interval, say 100 milliseconds at a time, and they're used for communicating a range of things. By communicating at a fixed interval, you implicitly get liveliness checks of each node included in the protocol. So that means you know that if you haven't seen something and you're communicating every 100 milliseconds and you haven't seen something for 300 milliseconds, you haven't gotten a message, you can assume that after 3 probes, it's possibly done. Now, in the case of service discovery, this approach seems pretty scalable. Think of this orb as a node of our service. It's going to connect to other peer nodes and tell everyone that it's alive and able to serve requests at a particular IP. It starts in the middle, connecting to a handful of peers, and it discusses its arrival and information about the service, what the service represents, and all of that state propagates across the cluster. You can keep adding and removing nodes, since each node is only concerned about the handful of others within its vicinity. Messages will eventually propagate throughout the entire system. Because the messages are distributed to multiple peers and spread, there is implicit replication built into the system. If one of the nodes disappeared, the messages won't be lost. Messages will still be replicated to all the other nodes due to the multiple connectivity. Everyone now knows that this account service is alive and available everywhere because the green state propagates throughout the entire system. And as you add more and more nodes, you run into a few issues. I want to highlight two in particular. Firstly, getting a message out to all nodes requires a lot of hops for the state to propagate fully. If you gossip changes at a fixed interval, it could take some time before every other node in the system is aware. Even when you gossip really frequently, you're going to have bottlenecks with network jitter, packet loss, propagation delay, which can slow you down. This means that your time to converge, the time for every node to know that this state has occurred, can't always be bounded or even fully controlled unless you have the perfect networking environment, and how we'd all love that. If you're really doing a lot of changes rapidly, if you're doing like Dropbox style tens of thousands of changes every second or every minute, you might get into a position where one particular state change never gets replicated to all nodes before the next state change has been generated and starts being replicated. You can try and tackle this by increasing the number of connections to peer nodes, and this increases the likelihood of being infected earlier on. But here's where you run into the second issue. Each of these connections increases the communication chatter back and forth. Any node can be infected with a state by any one of its connections, but you're going to have a lot of duplicate messages propagating through the system to nodes which are already infected. And this can be costly in terms of network bandwidth and overhead. Assume that every node in the absolute worst case was connected to every other node in the system. This would be pretty good in terms of your connectivity because you would be able to get any state change in one hop. So you could possibly put some control around how long it takes for stuff to propagate. Now, in a concrete scenario, imagine we had 100 nodes and they were gossiping every 10 milliseconds. That's over 1 million messages a second. And the number of messages grows quadratically as we add more nodes. You might get into a state where you're actually spending more CPU time and network gossiping messages about your system than actually serving requests. Now, luckily for us, some really smart folks have been thinking about these problems for a long time. There's a whole suite of papers, research papers going into this and trying to reduce this quadratic growth into something which is a bit more linear, or O1, which would be the best case. There's a particular paper I want to highlight. It's called Scalable Weakly Consistent Infection Style Process Group, or SWIM for short. And it's quite novel in some of the approaches that it uses in optimizing message bandwidth and improving detection of failures. There's a whole suite of mathematical models that are presented in the paper, none of which I'm going to try and repeat now, because I would not do them justice, where you can optimize network usage based on your tolerance for failure. Now, in practice, every heartbeat also propagates information about the cluster state. This means that bandwidth is used more efficiently by combining health checks to connected peers, whilst also gossiping information about state changes in the cluster. So a node will send periodic pings randomly to other nodes in the cluster. So in this particular example, node 1 is checking if node 2 is alive, but also takes the opportunity to inform node 2 of an addition, a state change in the instance of the account service. Node 2 replies that indeed it's alive and processes the update in the state. We've managed to propagate the state change and get a heartbeat in one round trip of messaging, which is pretty good. Now, the SWIM paper also gives a solution for making failure detection more robust through the concept of suspicion. So what we can do is we can suspect that a node is dead rather than outright declaring that a node is dead so to improve the false positivity rate. So in this particular example, node 1 thinks that node 3 is dead and tells node 2 to check by requesting an indirect ping to node 3 to reduce the false positive rate. And by arousing a suspicion from node 1 to node 2 can do its own independent checks and confirm or deny whether node 3 is dead. So this has a few benefits. Node 2 has been able to do, you've been able to add one more check to reduce the false positivity rate, but you've also been able to propagate to node 2 that a particular other node is dead. So you've been able to propagate the state change whilst you're at it as well. So you've improved resiliency to partial failures, whilst also improve and reduce the amount of messaging you need to do. So that's all well and good. And if you're going to go with an eventually consistent system, you can even go simpler and have a pull-based approach, where your clients just pull service discovery information on a timer from a central registry. So for example, I've made a particular example from a system that we use at Monzo. We have a config provider. This is just a provider of configuration, and the config provider can be implemented in many ways. It can be eventually consistent, backed by a gossiping style system, or it could just be backed by a sequential system or a strongly consistent system like Etcd. This is similar to how Envoy works. So Envoy, for those who aren't aware, is a service networking proxy that you put in front of your services. And its goal is to abstract pulling discovery information, load balancing, retries, circuit breaking, and stuff like that into a lightweight and robust proxy. And typically you run Envoy alongside each instance of your service. It pulls this dynamic configuration such as endpoints and routes from a config provider that you specify, like the one that we have. And if you have lots of Envoy instances, they will eventually converge. Not all at once, and there's no ordering. So say you have a service running and serving traffic at version 1. It's now time to release version 2 of your service. You're never, ever going to cut over 100% of your traffic at one instant point in time. You're going to do gradual rollouts and move percentages of your traffic from one to the other. This means that for eventually consistent discovery system, in practice, it will pretty much converge within the lag time that it takes for you to migrate all of your traffic over as a human to do your deployment. Now, what happens if something fails or there is a lag in getting all the latest information? The system, to a large extent, just keeps humming along because, as well as service discovery, it's got stuff like retries, circuit breaking, load balancing, all built into the proxy itself, and that's all in play alongside your service discovery. In strongly consistent systems, even things like a critical node failure won't be picked up immediately. There's always lag when doing things like health checks. You still need to do a few probes before you can declare a node to be dead. At Monzo, we have over 1,300 microservices and thousands of instances and replicas. And we see Envoy converge typically within a few seconds. So in summary, the takeaway is with service discovery, you can go with the level of consistency that you are comfortable with. If you need to prioritize agreement of your cluster, if you really need that consistency, you can go with a strongly consistent system. But in most cases, when you're doing service discovery, eventually consistent works just fine because every other part of the service discovery pipeline is not 100% instant. It is eventually consistent. There is always lag time. As always, run tests and simulations in your environment. This is our office dog, Bingo. And this is him after a hard day of testing the resiliency of cardboard boxes. Be like Bingo, run tests and simulations in your environment. And thank you.
So we have time for maybe one question, maybe two. Any questions?
Is Monzo operating in Ireland yet?
Because
you weren't the last time I checked.
We're not operating in Ireland quite yet. Never say never. Yes, I mean, there's a lot of complexity involved. The majority of it is not tech, and there's a bunch of regulatory reasons which we need to fulfill. But yeah, potentially, I can't make any promises. I'm only involved in the tech.
You just want one of those almost glow-in-the-dark cards, I know. Right?
Yes. But I think we have the next best thing. I have stickers.
Oh, okay. So we'll send people your way to get stickers. Any other questions? If not, thanks, Suhail, once more for his presentation.
Thank you.